Hello, welcome back. So in this part, now we will solve the next step, which is about the design of shear reinforcement. So in the previous part, we have discussed about the requirement of, we have checked whether our beam is required shear reinforcement or not. So we found that shear reinforcement is required. So now in this step, we will design the shear reinforcement. So maximum shear force for that our beam is to be resisted is 80.78 into 10 raised to power 3. So how much shear force is resisted by our beam? The concrete in our beam. We have to find out that. So shear force taken by the concrete, which we represent as VC. So VC is the stress, permissible shear stress in the concrete multiplied by the effective area of cross section. So permissible stress of concrete we have already calculated, which is 0.35 multiplied by the effective area of cross section, which is 40250 Newton. So which means this much shear force is resisted by our concrete. Now the remaining shear, while the maximum shear force is this one, so we have to resist this one. So now we have to find out how much shear force is to be resisted by the steel reinforcement. So the shear force which is to be resisted by steel reinforcement will be calculated as V minus VC. So this is the maximum shear force and shear force resisted by the concrete. So the remaining shear force will be 40530 Newton. So this shear force is to be resisted by shear reinforcement. So for this much shear force, we need to provide the shear reinforcement. So we know that shear reinforcement is provided in the two form. One is by the bent up bar and second by the vertical stirrups. So as we know that we have bent up two bars. So we will find out the contribution of the bent up bar for the shear force, and we will check whether vertical stirrups is required or not. So we will calculate here. So shear reinforcement will be provided in the form of vertical stirrups and the bent up bar. So as we have provided two bent up bars, so we will find out the theoretical contribution of these two bent up bars, which are of 20 mm diameter. So from the IS code, I have explained earlier in lecture 11 also. So this is the formula that we use to calculate the theoretical contribution of the bent up bar. And generally we bent up our bar at 45 degree. So this alpha will be 45 degree. So sigma SV will be similar to the sigma ST value, which will be same. And ASV here will be the value of, sorry, I forgot to include the 2 because there are two bent up bar. So ASV will be area of cross section of the bent up bar. So there I forgot to provide 2. So we need to include this 2 also. And after calculating, this value will also be slightly different, slightly more. Actually it will be the 2 times of this value. So this will be around 20. This will be around 20 something like this. So this will be around 204 kilonewton this time. So this much shear force is resisted by the bent up bar, but this is actually the theoretical contribution. We may not consider this the whole contribution by the bent up bar because IS code has recommended some other parameters also. So now we will check that. So again, please do the correction here. So this is 204, approximately 204 kilonewton, and there we need to include 2 into pi by 4, 20 square. So as I said, as per IS code recommendation, the contribution of bent up bar cannot be more than the half of the shear force which is to be resisted by the shear reinforcement, which means Vs dash value should be less than or equals to Vs by 2. So as the contribution is more than 204 kilonewton, but we are restricted to have Vs dash value as 20265, which is 20.265 kilonewton. So we will consider only this much contribution of bent up bar only, and the remaining shear force will be resisted by the vertical stirrups. So now the shear force for which vertical stirrups are to be provided will be the remaining half, this one. So we will design our shear stirrup for this much force only. So in the shear stirrups, first we will assume the dia of stirrups and we will find out the spacing of the stirrups. So that is the thing that we need to find out. So for vertical stirrups, we will assume 8 mm dia, two-legged. And once we assume the dia of stirrup and the leg of stirrups, so we will find out the spacing. So spacing can be calculated by the formula which is mentioned in the IS code in Annexure B. So you can refer to the Annexure B. I will not be showing because I have already explained the process in lecture 11. So you can refer to that if it is not clear to you. So SV is calculated by this formula. So putting all the values here, so we can find out SV as 524.58 mm. So this is the design calculation, design value. Now we will also find out the spacing from the minimum shear reinforcement criteria also. So from the minimum shear reinforcement criteria, on page number 48 of IS code, you will find out this formula. So using this formula, we can find out the value of SV as this. So 362.78 mm will be the spacing as per minimum shear reinforcement recommendation. Now, beside this, there are two other limitations also as per IS code. So basically, we can say that as per IS code recommendation, spacing of vertical stirrups shall not be greater than the least of 300 mm. That is one aspect. Second is 0.75 times of D provided, which is 345 mm. C is 524. So this is the value that we have calculated as per the design calculation. And D 362.78 value as per minimum shear reinforcement requirement. So the least of all four is 300 mm. So what we will be doing is we will provide our shear reinforcement, I mean vertical stirrups, at the rate of 300 mm center to center spacing. So this is what I have written here. So providing vertical stirrups as two-legged 8 mm dia at the rate of 300 center to center. So this is how we designate the vertical stirrups spacing. So now step 11 is completed. We have calculated the design. I mean, we have designed the shear reinforcement. And in the diagram, you can see till now we have the cross-sectional area of the beam, and we have designed the number of bars, and now we have designed the stirrups also. So in the step 12, we need to check whether side face reinforcement in the beam is required. Well, what is side face reinforcement? That we will see in the diagram. Generally, this side face reinforcement, it actually depends on the depth of beam. When the depth of beam is large, in that case, the beam may be subjected to the torsional effect and some other secondary effect also. So to counter that, generally we provide side face reinforcement only when the depth of beam is more. So as per this clause of IS code, so IS code has mentioned that. So okay, I will show you the same clause in the IS code also. So on page number 47, you will find out this clause, which is side face reinforcement. So there you can see it is written clearly here, where the depth of web, well, this actually for our beam, it will be, okay, I will be making here. So this depth, it is talking about this depth, effective depth. So this is actually the web. when the depth of web in a beam exceeds 750 mm. So when the depth of beam, this depth of beam exceeds 750 mm, the side face reinforcement shall be provided along the two faces. The total area of such reinforcement shall be not less than 0.1% of the web area and shall be distributed equally on two faces. Now I will be showing you with the diagram where this side face reinforcement is provided. So in the diagram you can see, generally we provide side face reinforcement here. So this pink bar, you can see this is showing the side face reinforcement. Well, in our case, our beam depth is 460 mm, which is less than 750 mm. So this side face reinforcement is not required in our case actually. Okay, and by chance if it was required, then generally we provide reinforcement on both face equally, and their spacing should not be less than 300 mm. I mean, it should not be more than 300 mm, or I mean this spacing. So it should not be more than 300 mm. So, but because side face reinforcement is not required in our case, so I'm not considering all these things, but I just explaining this so that you understand how side face reinforcement is provided. So as the depth is less than 750, no side face reinforcement is required in our case. Now the last step is about the reinforcement sketch. So till now we have designed our beam. Now we have done all the calculation related to the design of doubly reinforced beam. Now in the last step we make the sketch. So this is the sketch that we are supposed to make. So in this case, this is the beam. These green bars are showing the stirrups, and this is the bent up bar. This blue bar is basically the compression bar, and outer side it is here. So that is why this bar is only showing, and this bar is bent up bar, and this one is the bar on the support. And on the mid span, maximum number of tension bars is there. So on the mid span, when we cut the section, so the section you can see cross section, so all the bars are there. So this is how we do the dimensioning. In the bar you can see here, when we see the cross section 2 so at that point only the support bar, 2 bars are there, while 2 bars are bent up, which get on the compression side. Okay, so sometimes if the bars are down, sometimes we provide the spacer bar also to make the this spacer bar. Sometimes we provide spacer bar so that they can be accommodated properly. So this spacer bar can be shown here. So this spacer bar can be here so that they can be differentiated. Okay, so this is the diagram. So this completes our solution. Thank you.